Okay, let's now look at the multi-category single layer perceptron. Just to remind you, so this is the a perceptron with an input pattern x1 to xn, and we want, instead of having a certain, so when the activation w1 x1 plus w2 x2 plus wn xn, the activation, the net activation is greater than a certain threshold, then the perceptron would fire, meaning that it will go to +1. If it is less than that threshold or bias, then the output is -1. And instead of doing it this way, we put the wn +1, which is the bias, at another input with the xn +1 equal to -1. And then we have the augmented input pattern. So in the case of a multi-category single layer perceptron, so we just have one single layer, but we have a collection of these perceptrons. So this is the first one, the second one, and the third one. And the goal is, if you have an input pattern x, this is an x vector, so this is x1, x2, x3, and so on. So this is not just a value, this is the vector, the input vector. And this is the y, is the augmented input vector, where we have -1 here, where the weight, the corresponding weight, corresponds to that bias or to that threshold. For this one, for this perceptron, for this perceptron, for this perceptron. And so the outputs, because we're dealing with TLU, a threshold logic unit, so the output is either +1 or -1. And it will be 1 for, so if we have a number of possible outputs, so it'd be 1 for just one pattern, and then -1 for all the other ones, for j equal 1 to r with j different than I. Okay, so for example, if the features correspond to a cat, so this would be 1, and the others would be, the other outputs would be -1. If it's a dog, and this is the class for dog, so we will have 1 here, and then -1 for all the other units. And the way we adjust the weights, so the same way, we have a supervisor, a desired output, and we adjust the weight following this learning rule. So the new weight is equal to the old weight plus half of C D minus O Y, where DI is the corresponding desired output for for neuron I. The OI is the actual output for that neuron I, and the Y is the input pattern, and C is a constant. So if we have this example where we have a single layer of neurons with 3 nodes, with 3 perceptrons. So this is our output, the input pattern, sorry, x1, x2, and -1, where this is, again, these values correspond to the threshold for unit 1, which is 5 in this case, threshold for neuron 2, which is 2, and threshold for, or bias for perceptron 3, which is 0, okay? And then these are the final weights. Assume that we've finalized the training of our single layer perceptron. These are the final weights. And then if we look at the problem in the 2D input pattern case, the 2D input space or feature space. So this does not correspond to W1 and W2 as opposed to where we were looking at how the training or learning is performed. So this is, we're in the input space, X1 and X2. And then we have 3 patterns. Pattern 1 with input X1 equal to 10, X2 equal to 2. And we know that this pattern here belongs to class 1, meaning that O1 has to be 1, O2 has to be -1, and O3 has to be -1. So it's 1 for that particular class, as opposed to P2, where X1 equal to 2 and X2 equal to -5. Then the output, the corresponding output, it belongs to class 2, which is, that's why we have 1, and the other outputs are -1. P3, the third pattern, -5 and 5, and this belongs to class number 3. And then after we train our network, we find that these are the final weights, meaning that 5x1 plus 3x2 minus 5 equal to 0. Okay, and this would be the decision boundary in this case. And the same thing for the other decision boundaries, for this one, and for this one. Okay. And then we can see here that we have some indecision regions, which are regions where no class membership of an input pattern can be uniquely determined based on the response of the classifier. So these are the shaded regions here. And as you can see here, for example, for point Q, which is here, the response or the output is 1, 1, and -1. And that's not possible because our response is supposed to be 1 for only one output, okay? However, no patterns such as Q have been used for the training in this example. We didn't train this, so we didn't, otherwise it would be confusing for the single layer perceptron. Now let's find or see how we can get our weights. So this weights 5, 3, and 5 here, and the same thing for the other weights. So if we assume that C equal 1, this is our C, which is used for the learning rule. So and then our initial weights are equal to 1 minus 2, 0 for the first threshold logic unit. So, and then for the second threshold unit, this is the weight or initial weight. For the third threshold unit, this is the weight. So this corresponds to the first iteration, or actually the initial iteration. Now, if we feed pattern Y1 as an input, so if we feed this point here, 10, 2, -1 as an input, so this is our 10, 2, -1, with this initial weight for threshold logic unit 1 minus 2, 0, we find that the output is supposed to be 1. Now, if we do the same thing for the second, for that same input pattern Y1, so it's 10, 2, -1, but then for the second threshold logic unit, so the corresponding initial weight is 0, -1, 2, the response is -1. And the same thing for threshold logic unit 2. But we know that this pattern 1, is supposed to belong to class 1. So we're supposed to have 1 here, and -1 and -1 here. But then we don't get the -1 here. We know that the desired response here should be -1. So since the only incorrect response is provided by the third logic unit, we have to keep the weights for the first threshold unit the same, so we don't change them. So the weight in the second, after training, would stay the same. Same thing for the second threshold unit. But for the third one, we have to apply our learning rule, which says that it is the old weight, so 1, 3, -1, which is the initial weight, minus the input, okay? Because we assume that C equal to 1. So minus the input pattern, which is 10, 2, minus 1. Okay. So we get this new weight for threshold logic unit 3. Now we feed the second pattern, Y2, which is this one, 2 minus 5, 2 minus 5, and we have the minus 1 for the last, for here, for this last input. So we use the weights for the first threshold logic unit, so we didn't change them. So they stay the same, 1 minus 2, 0. And then we use the weight for the second threshold unit did not change also. So it's 0, minus 1, 2. So we use them the same. But for the third threshold logic unit, the new weights are minus 1, minus 9, 1, 0. This is the new threshold logic unit. If we apply these weights to our input pattern number 2, we find that the corresponding output is 1, 1, and minus 1. And we know that the second pattern 2 belongs to class 2. So this is supposed to be 1, and these two are supposed to be minus 1, but then the actual output for the threshold logic unit is wrong. So we have to adjust the corresponding weights. And the same way, we use the old weights for threshold logic unit 1, which were 1 minus 2, 0, 1 minus 2, 0, minus the input for this pattern here, which is 2 minus 5, minus 1. We get the second, the new weight. We keep doing the same procedure. And then after the fourth iteration, we realized that we didn't achieve convergence. So what we do is we go through another cycle of patterns. So we finished with pattern number 3. So we have to do it again for pattern number 1, pattern number 2, pattern number 3, and we adjust the weights until we reach the final weight for example, the first threshold logic unit after nine iterations, and we got 5, 3, 5. And this is what we got, if you remember, in here. So it's 5, 3, and 5. Okay. So that was the case of a threshold logic unit where we had an input of 1 plus or minus 1. If we have a continuous bipolar perceptron, where this is a bipolar sigmoid, then we've seen that the way to adjust the weights is given by this learning rule, and this is applied for all the threshold logic units. So from 1 to R, this one, and again if we feed an input which belongs to class I, then the desired output should be 1 for that class and minus 1 for all the other ones. So the concept is the same. So if we compare between the perceptron and the Bayes classifier, so the perceptron operates on the premise that the patterns to be classified are linearly separable. Otherwise, the training algorithm would oscillate. And then while the Bayes classifier can work on non-separable patterns. The Bayes classifier minimizes the probability of misclassification, which is independent of the underlying distribution. The Bayes classifier is a linear classifier on the assumption of Gaussianity. So if you assume that you have Gaussianity, then the Bayes classifier is a linear classifier. The perceptron is non-parametric. You don't have any parameters that you need to feed to your perceptron, but the Bayes classifier, so the perceptron learns just from the data, while the Bayes classifier is parametric. So its derivation is contingent on the assumption of the underlying distributions. So for example, you assume a Bayesian classifier, you compute use the Bayesian learning rule and so on. the perceptron is adaptive and simple to implement as opposed to the base classifier. Now I have some appendices here in with the notes where for a given cost function, I was just trying to find the learning rule, applying different optimization techniques, the Newton method, the Gauss-Newton method, and the linear least square filter, LMS algorithm. I also have the perceptron convergence proof, which shows that that if you have a perceptron, so after a number of training, you will reach convergence. So that, okay, so where is it? So this is the basically conclusion is, this is a proof that the solution exists. The rule for adapting the synaptic weight of the perceptron must terminate after at most n iterations, under certain conditions. Thank you.